All right. Hi, everyone. I am Radhanath Kundu from Manipal Institute of Technology, and along with me is Gordon Watts from University of Washington. Today, we are going to talk about using Python, coffea, and ServiceX to rediscover the Higgs twice. So, what Higgs we are talking about exactly? We are talking about the famous Higgs boson that was announced 9 years ago by both the experiments, ATLAS and CMS. And both of them release their data and the source code to reproduce the analysis. And today we are going to attempt the same. So we are going to attempt the same using ServiceX, FunkADL, and coffea toolchain. So this is the pipeline that we are going to use. First of all, using a Jupyter notebook, we are going to send a query code to ServiceX. ServiceX takes note of which data set is required from CMS Open Data and takes it in. It then slims it down so as to fit the query code and saves the slimmed down data to the disk cache. Then the data is sent back to the Jupyter notebook or directly to coffea, depending on whichever is more efficient. And then the analysis code is sent from Jupyter notebook to coffea. The coffea runs the analysis code on the data using a local or Dask or FunkX runner, and then sends back the result. So this is the whole pipeline. So what's CERN Open Data? CERN Open Data is a data repository for the public LHC data. It has over 2 petabytes of data and thousands of data sets. This is an overview of ServiceX. ServiceX takes in the data set from various formats like XAOD, NanoAOD, flat and tuples, and then it takes in the user query and slims down the data and sends it back in form of data frames, awkward arrays, etc. Now Gordon will take you over the rest of the pipeline.
So coffea is a lightweight processing framework and toolkit written in Python. It's built to process columnar data, but at the same time give you an event-wise view. The toolkit actually contains a lot of extremely useful utilities, paradigms, and approaches. But for the purposes of our talk, there are just a couple of things that features that we wanted to pull out. One is it's built to process files. It has distributed processing built into it, although we are only going to reference that in this talk. And it's got a very flexible data model, and you'll see that in evidence as we switch between columnar and event-wise views of the same columnar data. Next slide. We're going to look at 3 different notebooks in this talk. One is an introduction to FunkADL, ServiceX, and coffea. The second is using the ATLAS public data to remake the ATLAS plot. And the third is to use the CMS data to remake the CMS discovery plot. There is, okay, I'll get back to that. First, the other thing that both of us wanted to mention is this is very much a team effort. This should not be seen as just the 2 of us doing this work. There are places where we've outright stolen code from other people's projects. We've given credit in the repository, but I just wanted to make sure that we acknowledged many of these folks. In particular, I want to mention that Mason, who is the author of the Uproot backend, is going to give the next talk, and he's really going to make the FunkADL language, which we'll see in a moment, sing in a way that we will not have time to discuss in this talk. Okay, next slide. It is possible to run this yourself. The tutorial is GitHub is linked at that top link, and that goes directly to the talks subdirectory, which has the 3 notebooks that we're going to show here. There are instructions for setting up in the repository at the very top level, but as you'll see, there's some very much beta software involved. We're happy to give out the ServiceX endpoints. We just didn't want to put them in the repository for all time. They're unofficial at the moment for accessing the open data. We're working towards production versions. Some of the integration with coffea is beta, although all up on GitHub. And probably the most important point is it's not obvious to us that the CERN Open Data Portal can actually serve the data at the rate that ServiceX really wants to ingest it. And we'll make a few comments about that. And finally, unfortunately, Binder is not supported. And the reason is ServiceX for data download uses a non-standard port, and Binder only allows external access on port 80 for very reasonable for reasonable reasons. Okay, is that the last slide?
Yeah.
All right, so let's switch over to the notebooks. I wondered if I could ask the organizers if, could you stop screen sharing? I wonder if I asked the organizers, it looks like we started a little bit early. Does that mean that we have a little more time, or are we trying to keep things compressed?
I suppose, I think, yeah, finished about 5 minutes early on the last talk, so we can give that extra 5 minutes to you.
I can go to 8:20 is what you're saying. Sorry, to 20 after the hour, I think. Okay, that sounds good. First, let me ask if I have increased the size of the font enough that everybody can see.
Yeah, we can see properly.
It looks good. Okay, fantastic. All right, so let's get started with our first notebook. This is going to be fun, but it's also going to be fast because, as you might imagine, looking for the Higgs is a relatively complex operation. The very first thing we wanted to do was to demonstrate the pieces of that data flow diagram that Ina showed earlier in the slides. So the first thing I have to do is set up my environment. And if you look carefully, you'll notice there's something that refers to the CMS run one data. The CMS released it as AODs, and there's something refers to so-called an uproot data. Uproot data is a pseudonym for flat root files, and Atlas released its Higgs data as flat root files. So flat root files are perhaps conceptually the easiest to understand, so let's start with that. So the very first thing we need to do is we need to tell the system or ServiceX where to go find the files. Let's just look at a single file. This is going to be a Higgs signal, 125 GeV Higgs decaying to ZZs, one of them off shell, and then to 4 leptons. All right, so all I did there was declare a source of data. I didn't actually do anything. So the next thing we're going to do is run the actual query. So this here is the important part. What we're going to do is run it against a live instance of ServiceX. Right now, ServiceX took this query, which is going to select lepton PTs. It spun up a series of containers on a Kubernetes cluster to ingest the data, and then it takes that data, the Atlas n-tuple, which, as you might imagine, holds many, many, many different columns of data, and selected out a column called lepton PT, turned it into a so-called, shipped the data back to us locally on my laptop here in my my family home where I grew up, where I am right now, and converted it to an awkward array. And at the very last line there, you'll see that we printed it out right here. Now, it's a standard awkward array, and you can see it's just a series of numbers, which are all of the lepton PTs, but they're stored in MEV because that's the way Atlas works. Now, one thing that's very important for this talk is most of the time we will not actually go out all the way to ServiceX. By running that, it caches it locally. So if I rerun this, you'll notice it's instantaneous. Whoops, I should have printed out R again, I apologize. It's instantaneous. There was There were no indications it was going out to ServiceX. And that is, of course, the role of this ignore cache. And this means, this is because some of the ServiceX queries we have in here are running against terabytes of data. We cannot complete them in the time of this talk. Okay, so that was a call out to an actual, to the running ServiceX instance. If this was a computer that had nothing on cache, every single one of these queries would go out to that ServiceX instance. What's returned is a regular awkward array. As you can see, a lepton PT with one element per event. So it's got 164,000 or 165,000 events. We can plot it. I'm using the hist package, which is a very nice Python histogram package based around a core of C++ code and Boost histogram, which is a histogram in the famous Boost library. Looks exactly as you expect if you brought back the lepton PTs with no cuts. All right, it's really not the muon PTs, it's the lepton PT. All right, perfect. So what if we wanted to get back more than just the lepton PT? So let's get back the ADA as well. And you can see what the structure is. It's two columns, one of the PT and one of the ADA. Simple enough, but much more interesting maybe is what if we only want to get central electrons? One of the advantages of ServiceX is that it's in a big cluster in a facility somewhere. It's all written in Python, by the way, but and it is near a very large data pipe. I am not. I'm at the end of an ADSL line. So what I'd really like to do is limit the amount of data that comes back to my laptop or into my analysis facility if I was running on an analysis facility. So here, let's take the leptons and let's cut and only bring back the central leptons, that is the ADA with less than 1.0. All right, so if we do that, again, notice the same number of events come back because we made the cut on leptons, not on events. So let's look at a plot now where we look at the number of leptons as a function of PT. Again, I have muon track, it should be lepton, I apologize. So you'll notice we filled it twice. Once where we used all, so that's this line here, we're using the first result. And the second one here is where we used our cut, which pardon me while I scroll just a little bit too much, we use our cut coming back. Look at that, that's an error. Okay, there we go. Okay, so we've done that, and you can see the effect of the cut. It dramatically reduced the number total of leptons that came back. All right, and we can, we can make, I had a new motherboard installed in this last night, so there may be some weird things that come up. You can make same plot of that data and just count the number of leptons in the data. You'll notice that from ATLAS, it came back, everything when you make no cuts comes back as 4 leptons. That's because the data is highly skimmed that they showed, they stored for open data. And you can see this skew down low when we make the cut on ADA as many leptons get dropped because we've made such a tight central requirement. Okay, Ineth is going to talk a little bit about doing the same thing, but doing it from CMS run 1 AOD files instead of the ATLAS files.
Yeah, so you saw how ATLAS was doing it. Now for CMS, there are few differences that you have to keep in mind. First of all, if you want to do it without ServiceX, you will have to install a old version of CMS SW. Now that version comes in a VM or a Docker, or you have to install the whole source along with dependencies, and it is a very complicated step. Second, the data in these files are row wise and not column wise, like in the case of AOD files, ATLAS AOD files. And the third thing is that the data sets are very huge. It's like 7 TB for some of the data sets, and it takes about 30 minutes to run on ServiceX when they are working well. For your personal PC, I don't know how much it will take, and it will not, you will not be that patient, of course. So we will be using data from an earlier run, and that has been locally cached because that will take us a lot of time to run in our case too. So let's look at the query. It is the same query that we showed you for the Atlas side. The difference being we are using muons instead of leptons. So you can see at line number 2, we have used e.track muons, and that is one of the object that tells ServiceX that you are taking in a muon, but you are storing it in a track collection. If someone is familiar with CMSSW, they would know what I'm talking about. It's a special kind of collection for tracks, but since we are storing a muon, we also have to include the header files that pertain to muons to use the properties of muons. The second, after that, it's almost the same as Atlas side. Muon PT is taken out and is stored in mu PT, and then sent to the sent back from ServiceX. Again, if you see the number of events, it is different, but if you compare it with the cut on the eta, the number of events remains the same, because again, we are not working on the event level, we are working on the muon level. So the number of muons get cut off from the events, but the number of events remain the same. And finally, the histogram that you see, it is also skewed towards the lower side, as in the case of Atlas. So things to keep in mind when using CMS is that CMS stores all the muons, like in this case, all the muons or all the data. They do not clean it when storing it in open data, unlike Atlas does, because Atlas skims its AOD files because it's for educational purposes, and they don't want, they don't place all of the data in open data, only the amount of data that is required. Now Gordon will take you through coffee.
Okay, so let's talk a little bit about coffee. We've got about 10 minutes left, so I'll make this a little quick. And part of the reason is because a lot of what you've seen before about how we get the data out of ServiceX is just going to be repeated here. So what we have to do is bring together a query for ServiceX, the analysis code, which sits in coffea, and some sort of an execution policy, be it execute locally single-threaded, execute on DAS, or func-x, as was mentioned earlier. So this is the main way that we're using coffee. So let's look at that structure. The very first thing we do is we create a query in ServiceX. We'll call it selection atlas here. And all I've done is created this query. Nothing got executed at this particular moment. The second thing I've got to do is create a coffea analysis. So this analysis is dirt simple. It's going to create a histogram. It's going to grab the leptons that come from the event, and then it's going to plot the leptons. So it's basically the exact same thing that was done before, but now we've done it in a processor. And the beauty is if our data set had 20 files, Coffee would automatically split up those 20 files, run this processor on each of those 20 files, and then coordinate combining the results, and then returning a single histogram to us, the user. All right, so now we have to define the data set for Coffee to run on. It's very good at running on multiple data sets, so it requires us to do a little bit of extra work. I'm not going to go into the details of that. Finally, we also need a bit of boilerplate, which links together the processor, which will do the analysis, the execution policy, we're going to use local execution for here, and the data sets all at once. Again, this will query ServiceX and it will grab something local. This is just an example of what the result looks like. And you can see it's got here PT as one of the results, which is a histogram. And we can make a plot of that, which should look, at least to my eye, it looks identical to the plot that we had earlier on the Atlas data. All right. You've seen the framework now. This last piece of the example is exactly how both the Atlas and the CMS Higgs examples are structured. So we're now going to go through very quickly the ATLAS example. The ATLAS is only a half a gigabyte, at least as a zip file, all of their flat root files. So it's actually not a lot of data. So this is interesting from the point of view of how the analysis is structured. It's not interesting in the point of view, I get, as a challenge, at least for distributed computing. That will come with the CMS one next. Okay, so the very first thing is we have to build a query. And one of the aspects of the ATLAS analysis is we need to do a trigger selection. So all events have to be, we have to filter at the event level and select electrons or muons. The next thing we've got to do is we need to make different cuts for electrons and muons, but ATLAS piled electrons and muons into the same set of branches. So what we're going to do is build a lepton object. It's like we're building a new event data model right here. We'll build a lepton object, separate it into electrons and muons, and then make the cuts. This step builds the electron object right here. And then here, notice we take electrons. This is how ATLAS tells the difference between the electrons. There's something called the type ID. If you're familiar with particle physics, you'll know exactly what that's referring to. This is real data, not Monte Carlo, though, for those of you who get the inside reference there. So we separate into electrons and muons, and then we do a series of cuts. These cuts are pretty similar to each other, but you'll notice some differences, like there's a different eta cut that has to do with detector geometry. It's a slightly different track isolation cut as well. All right, so this is us defining the query. Now, one thing to note is that at the upper level, when we combine the 4 leptons into the invariant mass to search for the Higgs, we don't actually need all of this data that we cut on. So for example, ET cone, that can stay at ServiceX. No reason to bring that all the way back to the laptop here. So that's this final step where we declare the exact things that we want to bring local to the laptop. So we need the lepton, the electron and muon as separate things, along with some scale factors. All right, we finished defining the query. The next thing we have to do is define the analysis. I'm not going to go through this because most of this is going to be fairly, I don't know if it's sophisticated. To me, it was sophisticated when I wrote it, awkward array manipulations. So here, basically what we do is we do a final cut on the electrons and muons. We make an event mask, which checks that there are exactly 4 muons, or 4 leptons, which is what's required by the ATLAS analysis. We then make a ordered pre-selection cut. And then after that, we have to look at the EE mu mu, the EE and the mu 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 channels separately. For those of you not familiar with the analysis, don't worry about it. It's so much. It's just some extra code that means we have to split this into 3 different sort of sub-analyses. But we combine them all, fill the histograms, and then return them to coffea. So that's our coffea process. All right, so let's create a data set again. I'm using it slightly more sophisticated because I want to run on lots of data sets. Here are all the data sets that we're going to run on eventually. And then here is the boilerplate code I mentioned before, which brings together the execution policy. It brings together the analysis to do the actual running. And then finally, it also brings together all of the data sets, which is just a little bit off screen right here. All right, so let's run on a local version of just the same original file that we've looked at for the lepton PT before. And now let's make a plot, and lo and behold, there's the Higgs separated out by channel. All right, great. Actually, let's ignore that. So now let's run on all of the data files. This will take a second because it's running in a single threaded mode. It'll take more than a second. So it's now got to process data from each one of those files and then pull them together into an overall plot. There we go. So it was a little nerve-wracking. This plot isn't interesting from the physics point of view because it's got everything all piled together, but you can see sort of what the overall plot looks like. Much more interesting is, say, let's look at the data. And look at that little Higgs bump along with the more Z-like bump. But of course, the real question is that signal where we expect it? We've already looked a little bit at that. So that signal is at 125. And then let's look at just the backgrounds. And you can see the background has no peak around 120, which means that that data plot is looking almost the way we would expect. All right, let's look at the CMS version of this analysis. Sorry, this was meant to be at the top. Take it away, Adinath.
Yeah, let me share my screen. Is it visible?
Yes, sorry. Yes.
All right. So just like as you saw it in Atlas, again, the steps are pretty similar. We just a couple of differences. Again, I am going to repeat that we are not going to be running it in real time. The total data that is required is 70 TB. We could only get about 43 TB running for this notebook when we ran it the last time. This is because we told you that it takes 30 minutes for 7 TB when it's good, but the problem is that the CERN Open Data and ServiceX collaboration might not be working right now. So that's why we could only get about 43 TB. And ServiceX return locally is only 10 GB. So this is, again, we first set up all the libraries that we are going to use, and then we define the base query. So this is the line number. So this part, you might see it's written dummy. That's because we will put in the data sets later when we are running on all the data sets. So this is taking out all the muons, electrons, and the vertex position. So this might not be what you saw in the Atlas side, but this has a particular use on the CMS side. So when we are doing the cut on the muons and electrons to get the good muons and the good electrons, then you can see where it is used. It's used here, the I.P, to get the dxy of the global track of the muons. So this is the whole query that is run so that we could get the good muons. And like we said before, the number of cuts have to be more in CMS side because the data set is more and it is not cleaned as in the case of Atlas. So similar, the muon and electron have almost similar cuts, except for a few, but even they are similar on the base level. Then we take out all the properties that we require for muons and electrons. So PT, phi, eta, energy and charge. And then we go on to the analysis. So this is the analysis code. This is where we do the cuts and get the good muons. And from here starts Brian Cruz's code that we directly copy pasted into the notebook. So this whole code from here to up till here, sorry, not that, up till here is the whole code from Brian's notebook. And after that, we do some more calculation, and then finally we plot the Monte Carlo file. So this is just to run the analysis on the data set that we have. And this is the plot that we get from one of the Monte Carlo files. The mass is centered at 125 GeV, where we expect to find the Higgs. And this is not that interesting. When we run it on all the Monte Carlo and data files, then we get the bigger plot. This is where the Z is supposed to be 91 GeV and the Higgs is at 125 GeV. This is again Monte Carlo data set, and this is the whole plot of everything stacked on one at the top of another. After that, we were running the data set files, and you could see that Higgs is coming up but it's not complete, so we can't see a clear plot as in the case of ATLAS. But this is a work in progress, and you can see that the Higgs has already started appearing. So we plotted out the different signals, like this is the signal for Higgs only from the Monte Carlo dataset. And this is again, like we said, 125 GeV centered signal. We also plotted the background only so that we can see that it doesn't contain the Higgs. And like we said, if we subtract the background from the whole signal, we will get the Higgs plot that we showed above. So this is all the all the different particles in a plot except the Higgs. This is for again for the Monte Carlo dataset. And that's it for our presentation. We will take questions now.
Excellent, thank you. So we do have some questions over on the Slido. If one of you would like to bring up the
Sure. Could you send the link? I do not have a link.
Sure. Ben has quicker fingers than I do. He has just posted it in the Zoom chat.
There we are. Thank you. And let me share. All right. The interface does not look the same. Okay, I just got. Can you hear me?
Yeah, we can hear you.
Briefly cut out, but
message, I think. All right, I just got a Zoom quit unexpectedly.
Okay, let me share the
I
screen.
can share the.
I can share it.
Sure.
Is it visible?
Yes, that's visible.
Okay, how much prep was needed for this talk, or rather how much was real time, particularly the multi-sample Higgs mass plot? So yeah. After ServiceX was built up, we took about 3 or 4 days, like this week basically, to complete this talk. That was mostly because of the CMS data taking a lot of time, and even then we couldn't finish. But the ATLAS data would have taken much less, just the code and stuff in that part.
So sorry about that. My Zoom client crashed for whatever reason. I measured the ATLAS time from start to finish, and it was less than an hour to fetch it all from CERN EOS. Biden is completely right about the CMS data set. One thing we observed is the first couple of times we ran on the 10 terabyte subsamples, it took us just, it would take us about 30 minutes, 45 minutes. But I think we may have triggered some sort of rate limit, because by the end, the amount of data that we were getting back from the CERN Open Data instance was a trickle, and it slowed ServiceX way down. This is something that we'll investigate, but we don't fully understand where that slowdown is coming from yet.
Okay, so the next question is, what does the async keyword do? This is the first time I have seen it. So async keywords is used to run asynchronous function, basically functions that are not that can be run in parallel, and await keyword is used to make that function run in synchronous manner, and so that they are run in the way that we normally run functions, basically.
Why don't I take
something to add?
Oh, no, I was going to say the top question that just got upvoted at the very top of the screen, it shifted. So let me take that one. Who provides the computing resources on the ServiceX side? So we're running on a semi-test production cluster at University of Colorado. It's the so-called River cluster. It's part of IRIS-HEP. This is a large National Science Foundation software institute in the United States, and it has some resource, computing resources. I believe, I may be getting this wrong, I believe that cluster is of order 1,000 cores and has a significant amount of disk space associated with it. But this cluster was only using, these instances were only allowed to use up to 200 cores at once. But CERN Open Data was never able to supply us with enough data to actually use 200 at once. So the system never expanded. I think the highest I ever saw it was 18 cores were being used at once to process the open data for those 30 and 45-minute runs. We could have used more for a shorter amount of time if we'd been able to source the data that